Hello, welcome to the 9th lecture in ML series. In this lecture, we will be starting with a regression problem. Imagine you are trying to predict someone's weight based on their height, or estimating the house prices based on the size and location. These are all the kind of problems that you are trying to solve by using regression. Regression is a mathematical way to model and predict such a relationship between the variables. So we will be discussing a simple form of such a regression problem called a linear regression, where we consider the relationship between the variables as linear. So now so far in all our previous lectures we had considered the classification problem. Classification problem tries to predict the categories, that means yes or no, true or false, or red, green or blue, while the regression problem focuses on predicting continuous numerical values like predicting a weight, or predicting a house prices, predicting a stock prices, predicting a temperature, predicting some person age. All these kind of problems are regression problems. So the basic difference here is, if it is prediction of a discrete class label, then it is a classification problem. If it is predicting a continuous numerical value, then it is regression problem. So let us try to understand this regression problem with examples. So let us consider an example. Like classification problem, here also the actual output for a given input is given. So it is a supervised learning task. Okay. So let us consider here 4 students data is given, and for each student the number of hours studied and the exam score is given. Okay, and you are expected to predict the exam score of a student who studied for 5 hours. Okay, so to predict this, first we have to consider this data set, and from that it has to learn the relationship between y and x. That means it has to learn the relationship between exam score and the study hours. That we are calling it as a regression problem here. Okay, so what is the goal of the regression problem here? The goal of the regression problem is to find a mathematical function that describes the relationship between y and x. So that relationship might be a linear relationship, or a non-linear relationship, or a polynomial relationship. So a simple form of a relationship is a linear relationship. So let us consider a linear relationship, and a simple form. Simple form means where you have only 2 variables in the problem, like this problem, study hours and the exam score. So then it will be a simple linear regression problem. So in case of simple linear regression problem, we have to find a model that best describes the relationship between 2 continuous variables from a given data set. So one of the variable, so the variable for which you are going to predict, that you call it as a dependent variable, as it is dependent on x, and the other variable is an independent variable. So the goal is you have a set of xy points are given. The goal is to find a best fit straight line that can be later used for predictions. Now, to solve this problem, one of the design issues, that is, how are we going to represent a hypothesis? For representing a hypothesis, as we said, it should be a linear relationship. So we are going to consider a linear relationship. So then the hypothesis representation is theta naught plus theta 1 plus x. It's like y is equal to mx. Okay, where theta naught is the y-intercept and theta 1 is the slope of the line. So this is the hypothesis. Whatever the result of this hypothesis is y hat, this is we consider it as a predicted value for a given x1 value or a given x value. Okay, so when you have multiple features, multiple input features, then we call that as a multiple linear regression problem, where the equation you get it as a hyperplane, that is theta naught plus theta 1 x1 plus theta 2 x2 plus so on theta n xn. That is the hypothesis representation. In a vector form you can write it as this is a column vector into x. So this is a multiple linear regression. So we'll start with the simple linear regression problem. So the goal is to, given a data set, find theta naught theta 1 in case of simple linear regression, or in case of multiple linear regression, theta naught theta 1 to theta n, such that it best fits the data set. Now, how do you define this best fit? For that, we have to define our performance measure. The performance measure or the cost function is the one which is closest, right? So we need to somehow quantify the difference between the predicted and actual values. So to quantify the difference between a predicted and actual values, we are going to use error. Error is simply a difference between predicted and an actual value. So actual value minus predicted gives you an error, right? Now we can use that error, but we will be using a squared difference, not the direct difference, because squared difference always gives a positive value, while the normal difference sometimes gives a positive and sometimes gives a negative. The effect of positive and a negative over some training examples might cancel out. Okay, so to avoid that case, we are going to consider the squares of the differences. So that's why we have defined this performance measure or a cost function as a mean squared error. So in case of mean squared error, it is the average of the square difference between a predicted and actual values over all training examples. That is 1 by 2m into sigma I is equal to 1 to m, where m is the number of training examples. For each training example, y cap is the predicted value, yi is the actual value. So squares. Now 1 by 2m is for a mathematical convenience and to cancel while doing this differentiation, and we will discuss in detail, I think, when we discuss the derivation part. For the time being, you keep in mind that there is a purpose for each term here. Square, there is some purpose, and 1 by 2m also some purpose. Okay. Now, let us define formally this define this learning task. So you are given a data set. The learning algorithm task is to find a theta naught theta 1 that yields the smallest j of theta, smallest cost function or a smallest mean squared error. Now there are two approaches. One is a normal equation and the another one is a gradient descent. So by using the properties of the mean and a differentiation, we can do some derivations. From that we can get a solution to the normal equations, and then we can find out theta naught theta 1 values. That is a normal equation approach, and we will see how to derive those theta naught theta 1 which minimizes j of theta. And similarly we have the gradient descent method. This is a very popular and an efficient method, which is an iterative optimization algorithm which modifies the theta values, that is theta naught theta 1 in case of simple regression, in each iteration, such that the cost function is decreased. The theta are modified in such a way that j of theta is decreased in every iteration, and we will see how it can be done in the next lecture. Okay. Thank you.